All right, so this test is 15.1, 15.2, 15.3, and then 17.1 and 17.2. Okay, recall that 15.1 through 15.3 was about the bending and changing of light. Okay, we started with 15.1 with Snell's law, and Snell's law brought us to the idea that light changes its direction as it passes through different media. So, for example, as light travels through air, right? As light travels through air, it travels fast as possible, or as fast as it can on Earth. That's considered like the fastest medium. Pretty much air and carbon dioxide are the lowest N values, which is the fastest medium. As the N values go up, though, you get to water, which is 1.33. You get to glass, 1.5. All these table values you don't have to have memorized. They'll either be given on the test in the problem specifically, or I'll give you the table at the back of the test, one or the other. So you get to water and air, which are 1.33, water and then glass, 1.33 and then 1.5 respectively. What happens as the N value goes up? What did we talk about for using Snell's law?
If it's going from air to any material and it's higher, or any other material, then it slows down. So if it's going at this angle, we go to a lower angle.
Yeah, so when it goes from a lower N value to a higher N value, what happens? It slows down. Now, when the wave slows down, that means it bends toward the normal. So this is the beginning of 15.1 we're talking about right now. Okay, it bends toward the normal. And to show you a diagram of this so you can see what we're talking about, we've got air out here, and we've got water here. What happens is this beam of light travels, hits the boundary, and bends. It alters because of the wavefront slowing down or speeding up. So we might see something like this. Right here's the normal, let's say. Let's say coming in, it hits the normal. It's a pretty bad light ray. Let's make believe it's actually straight there. Hits the normal at an angle of like, I don't know, let's say 45 degrees, that is. Well, as a result, if it's going to go into something that has a higher N value, remember air's N value is 1. Water's N value is 1.33. So to go from one to the other, it means it has to slow down or bend toward the normal. So you can draw a diagram that's exaggerated if you'd like, but recognize that that angle that's there, this theta here, that angle theta is something less than 45. Something less than 45. Okay, that's what it means to bend toward the normal. The angle you're going to measure is always between the actual ray of light and the normal. So if it's bending toward the normal, it means the angle is getting smaller, right? Their light ray should do this. It should want to do this. Follow my marker here, ready? So it comes in this way, and it should want to continue this way. But it doesn't. It bends toward the normal. Okay? It slows down. That's always the case. And what happens in the other case? What happens in the other case? What happens in the other case? A higher N value to a lower N value. Katie? It speeds up. So as you could imagine, it bends away from the normal. And that is the case which gives you total internal reflection when it speeds up. Okay, when it goes from one that has a higher N value to a lower. Let's get to that in a minute. But before we do that, let's write down Snell's law so we can understand mathematically how we're going to have to be questioned in this section. So Snell's law tells us the following. Ni sine theta I equal Nr sine theta R. What does I stand for? What does the I stand for in Ni and sine theta I? Incident. Incident. Or some students have been thinking of I as initial. That's fine. You can think of it that way. And R is refracted, okay? But you can think of that as like the second material if you want. So I is like the first material, R is the second material. So if you want to use 1 here and a 2, or I and F, that's fine also.
Wait, this is like that formula that, what's the formula that's like, I'll think about it.
Think about it, yeah. It's like momentum, I guess. It's a product of two things, initial and final. So it is in nature like M1 V1I equals M2 V2I. You can think of it that way. But the idea of Snell's law is that we could calculate the actual angle. How do you calculate angles? What do you have to do to solve for theta? This is the part that people messed up, even on their lab.
Don't you have to use the sine inverse?
Yeah, if you're going to calculate an angle or solve for an angle, please make sure to remember to use the sine inverse. What does that mean? It means A, you need your calculators. B, you need your calculators in the correct mode. C, you need to use your calculators. Okay, not just have them here and have them in the right mode, but know how to use them. So if you haven't really been practicing much in class when we do these kinds of things, you better make sure tonight that you do practice so you understand how to use the sine inverse function. In addition to that, you guys have recognized already that in chapter 17, a lot of our numbers are in scientific notation. So this is going to be a heavy calculator test, or a calculator heavy test, whatever you want to say. But make sure that you understand how to use it. If you don't, come by at some point today and ask me. Okay, if you're not sure about how something works, please find me. I have a lot of frees today. So you can come by and ask me. I'll show you how to run through an example with scientific notation or something. Please ask. And honestly, if you're in doubt, you forget, just go to YouTube and type in how to use scientific notation, how to use inverse sine on a TI-83, and there'll be a video, I guarantee you, on how to do both of those. Okay? So the beginning of 15.1 was this idea of Snell's law and the bending of light. In 15.2, we specifically talked about what happens when light is bent so much that it doesn't exit the material it's in. Okay, and this is what we kept talking about, and I think your homework and your text, I gave you a few examples. A lot of them ended up with like the end value being 2.4, which was around diamond. The reason that was used a lot is because diamond exhibits this property. So certain materials, when light passes through them, wants to escape, but the light ray keeps bending. So let me demonstrate this with a little lab. This was the idea of that simulation you did on Snell's law. If I have an angle, let's say an angle coming in at like 20 degrees to the normal. Let's put our normal right here. If I had an angle coming in at 20 degrees, and let's say that we're going from cubic zirconia to air. Okay, cubic zirconia has an end value of around, I think, 2.2-ish. It might be a little off, but that doesn't really matter right now. N has a value, air has a value of n for 1. So if the angle trying to exit cubic zirconia is 20 degrees, and you're going to a material where it travels faster, like air, it means it bends away from the normal. So let's draw another angle on the other side of this. There's our normal first. Let's draw the angle on the other side, and let's exaggerate it. Let's draw it like this. And let's call this angle, hypothetically, okay, I don't really know what it would be. Let's just say it's some angle greater than 20 degrees. We know that. We don't know what the number is, but I'm going to put theta greater than 20 degrees. Why do I know it's greater than 20? Because again, it bends away from the normal. It bends away from the normal. Eventually, here's what happens. Eventually, if you keep increasing this 20-degree angle that's incident at the bottom here, if I keep taking this value and increasing it, this will bend more and more until it bends until it's 90 degrees. Until it's literally 90. Like right now, this might be what, like 70 degrees? Just based on the actual sketch. 70, maybe 75 degrees or so. But if I keep increasing this number, it's going to keep increasing this number until it bends at 90 degrees and it's along the surface. When that happens, that means that any point beyond that for this angle, any angle greater than the angle you get that causes this to bend at 90 degrees, is going to exhibit total internal reflection. Where the light ray, instead of passing through and bending, it bends it so much that it bends back into the material. And it never actually escapes the cubic zirconia. Okay, that's what causes things to sparkle or shine. The example I gave you in class, if you remember, were called light pipes. And light pipes are like fiber optic cables. Fiber optic cables carry a signal, and it carries it through the entire cable length by causing total internal reflection as the beam bounces back and forth on the interior walls. And you've seen this before. I put up an image, and it was like, remember the thing you see at like the carnivals? With there's no light at the very end of this little, like, it's like, what's the example? They're called swoosh, like the Nerf things that you had when you were a kid. They had all those like little like rubber things coming out, but those are the ones that you see at like carnivals that have lights on the end of them. And the light gets carried down the whole tube. You don't see any light on the surface of it because no light's coming out. It's all getting trapped inside. But at the very end of the tube, you can see the actual light. So this concept of total internal reflection occurs. It's really refraction, right? But it occurs when you go from an end value that's higher to an n value that's lower. That's the only way it could ever occur. How do we find that critical angle? How do I find the critical angle? There's two ways to do it. Two ways to do it. And?
You use the equation which is the sine inverse of NR over NI, or is it NI over NI?
Say again, n.
Is it NR over NI?
It's always going to be the smaller number on top. So it really doesn't matter, but in this case you can tell it's...
NI over NR.
Isn't it always going to be 1?
Well, we're going from cubic, air is always 1. We're going from cubic zirconia to air. So cubic zirconia needs to be on the bottom, right? So Ni is on the bottom, and R is on the top. Okay, again, we're going from the cubic zirconia, which is 2.2, to air, which is 1. The smaller material, or the smaller n value is always in the numerator, so if you forget which is which, but it's on your formula sheet, right? So you can use this formula directly, if you want to. Or, if you really would like to, you could just plug in 90 for theta r. Okay, you could do this. This is where this came from, if you recall. Okay, you could use Snell's law and set theta r equal to 90. And when something is the sine of 90, what does it become? 1. So this really drops off and becomes a 1. Okay, I'll put the number 1 up top there. It becomes a 1. Well, in reality, what are you doing now? You're just solving for theta I. How do you get rid of Ni? How do you get rid of Ni? Louder, divide. So divide NR over Ni. There it is right there. And then if you want to get theta I by itself, you get rid of the sine by doing sine inverse. Well, there it is right there. So we call this angle theta C, even though it's really the incident angle. It's the incident angle necessary to cause total internal reflection. Theta C is critical in the sense that anything beyond that value does indeed cause total internal reflection. So if you have any angle greater than, let's say the critical angle turns out to be 25, 26, 27, anything up to 90, from 26 or 25 up to 90 would cause total internal reflection. Okay? What else from 15.1 and 15.2 and 15.3 of questions about? We'll get to 17 in a second. We recently did that, so I want to ask about these others. Nothing on your problem set? No issues? No questions at all? You're pretty straightforward?
Is there any way to solve for n, or would you just give us a table of values?
If you solve for n, you would need theta I, theta r, and one of the n values to solve for the other n value. Now you could also always get n. Do you remember the formula that we used? It was like a quick formula. It was the speed of light. The formula was n equals the speed of light over the speed of that object in that material. So this is the speed of EM waves. So this was always 3 times 10 to the 8 over whatever the velocity is in the material itself. That'll give you the n value. Remember we showed this to prove that n is always greater than 1? Because the velocity you get here to fill in this blank with on the right, that v, has to be less than 3 times 10 to the 8. 3 times 10 to the 8 is the speed of light in a vacuum. That's the fastest speed we can obtain. So as a result, the other value, the denominator, must always be less. When the numerator is always bigger than the denominator, it proves to us that n is always greater than 1. Okay, that's a good point to bring up. Okay, conceptually a really good point to understand. At the speed of some material that's not in regular air, but maybe in water, has got to be smaller. So maybe this speed is just 2 times 10 to the 8 because it's suddenly in glass. Well, I know that that's going to be glass because 3 divided by 2 is 1.5. 10 to the 8 cancels. So this is clearly glass if I'm thinking about it because I happen to remember glass is a value of 1.5. What are the units of n? What are the units of n? What should the units be, Theo? Not newtons. Newtons would be a force, right? Again, guys, whenever you say newtons, you're assuming it's a force that you're solving for. N is not a force. Not coulombs. Just kind of throwing out every unit now. Think before you answer this. This is more logical reasoning. No, it's not. It's not a degree. It's not degrees, and it's not meters per second. No one knows what the units of n are? Here, make it easier. What are the units of c? 3 times 10 to the 8. What are they? And what are the units of velocity? Meters per second divided by meters per second. What are the units? It's unitless. Okay, like mu, unitless. Okay? No units for n. Because look, right, it's meters per second over meters per second. I didn't put them here on purpose, just to see who remembered. Look, meters per second, units cancel. Okay, n is a material property. It's a material property. It's really a ratio, similar in nature to mu. Mu is a ratio of FF to Fn, the friction force to the normal force, and it was really Newton over Newton. So as a result, mu, right, we didn't have to worry about having units because it was unitless because the newtons canceled. Other questions on 15? Yeah.
There was like a question on the problem sets. It was like also like the one we did in our notes where it was like from this distance, this distance, that distance. What do you feel like an example?
Sure. Is that 17 you're talking about, right? Chapter 17, part 2? Yeah. Let's go over that first, then I'll do an example of that. But any questions on 15? That's what I'm asking. On chapter 15, any questions still? You could expect, for sure, to have some sort of math problem on chapter 15. Okay? You could expect conceptual stuff about like the speed, the different n values, understanding that as, and you did a lot of this in your lab. A lot of you did well with this part. Understanding the relationships that exist. Right? As nr went up, what happened to theta r? You could solve this mathematically, you could understand it physically, or you could really analyze it using the equations analytically. So, there's multiple ways to understand that, but understanding that as the material property n changes, theta changes as well. Okay? I'm trying to think of what else in 15 I'm maybe forgetting. It's pretty straightforward, 15. I mean, the math part, make sure to practice, but the conceptual part, you have to just understand what's going on with the waves. Again, slowing down or speeding up. 17.1 was about 17.1. Yeah, it was the beginning of electricity. We talked about electric charge. And in 17.1, we didn't really have any formulas at all. But we did talk about a lot in 17.1. In 17.2, we had formulas. In 17.1, we talked about that constant E, right? The fundamental charge. This is not the same E as math class, by the way. You'll learn about a letter E like pi in math called the natural base. Logarithms? Natural log? Okay, but this is not that. This is the fundamental charge, 1.6 times 10 to the negative 19 coulombs. This is the charge on a proton or an electron, but obviously for an electron that charge is negative. For a proton that charge is positive. Where was this charge derived, or where did it come from? Anybody remember? We talked about it in class. How did we come up with this idea that the electron or the charge in general is quantized? There's an actual amount to it. It's not some random arbitrary number, it's discrete. It's always 1.6 times 10 to the negative 19. Or multiples of that number. You could have 5 electrons, and then suddenly it's 8 times 10 to the negative 19 coulombs. You could have 2 electrons, and it's 3.2 times 10 to the negative 19. What told us that that is true?
It was the oil experiment, right?
Yeah, the milk and oil drop experiment. The concept, if you recall, was that oil was dropped and it was charged by X-rays that were ionizing the air inside of the experiment. Those oil drops grabbed onto like some negative charge. Some of the oil drops floated when the parallel plates, the capacitor plates, were charged. There was a negative plate on the bottom. The voltage was turned on, causing a negative charge on the bottom. These negative oil drops didn't want to go to a negative charge. Why don't negative oil drops go to a negative charge? Why didn't the oil drops go to the negative charge? They repel, likes repel. So the object, the oil drop, did not fall to the bottom, yet it suspended itself in air. And based on actually where it suspended itself, the experiment led to the idea that the electron is in multiples, or the charges of all those oil drops were in multiples of this number right here. Since they were all multiples of this number, it meant that this number had some significance. That idea was then converted to say, oh, well, that means that there's like 7 electrons on this oil drop, and 5 electrons on this one, and 2 electrons on this one. So the charges on all those oil drops were multiples of this number as a result. Yeah. Bottom of your formula sheet. Yeah.
What was that question about? Was it more likely for a like charge or a positive charge to repel or to attract? Those on the questions
It
today.
needs to be different wording. That would make sense. What's the, pull up the exact wording. We also talked about in this section the idea of charging. And there are several ways to charge and materials that can be charged. So first, we talked about insulator and conductor. What's the difference between an insulator and a conductor? What's the difference? Ben? Ben. Pablo.
take it too.
You had your hand up also. I'll go Pablo. Come here next one. Pablo. And an insulator is? Yeah. So a conductor easily allows the flow of electricity to go through it. An insulator does what it says, insulates against electricity. By the way, insulator is also, you could have insulation on your house, which prevents heat flow. Insulation in electricity prevents electricity or electrical flow. An insulator does the same thing in both cases. It prevents some flow. Yeah.
So also you were talking about like a hybrid, so it was like
Yes.
both a conductor and insulator. So how would they like how do people control that?
Yeah, so usually with some sort of a diode, which is something that can change the actual poles. So it's an insulator that has been, I guess, infused with, it's the best word for it, infused with a certain metallic alloy usually. And that insulator can be turned from an insulator to a conductor based on the electrical flow that's actually placed on it. It's useful because certain times you might want a material to be an insulator to stop the flow of something, right? You might want it to reduce the flow, like it's called a resistor really in circuits, or you might want it to continue the flow. The other one that we talked about was called a superconductor. That what Klaus just mentioned was a semiconductor. Okay, semiconductor. That's what that is. And we talked about that in class. And then a superconductor, it conducts extremely well. It conducts better than a regular conductor with almost zero loss of friction. So when these, and it's tough to go over this right now because we haven't done circuitry yet. We're going to do that in chapter 18. But the concept is that these electrons are flowing through some sort of a circuit, usually made up of a conductor itself, like copper wires. And these electrons, they collide with the metallic atoms of copper, and it slows them down. It's got a natural resistance to it. Now, if nothing slowed the electrical flow down at all, it would have no loss of friction. It'd be a perfect world. Unfortunately, that doesn't happen, so you do lose energy. But what happens is that there are things called superconductors, which are pretty much almost no flow at all. Almost no resistance to flow at all or whatsoever. So those are your best bets to get something that would be close to negligible in resistance. After we talked about those types of materials, we talked about charging. You can charge by contact. What's an example where you charge by contact that we talked about? What's a simple one?
The balloon, like if you rub a balloon against your hair.
Yeah, something simply where you rub one material against another. That's usually an insulator. Okay, you can charge it by that contact, by that friction there. Yeah.
Does it count like if you're charging a phone? Does it count?
Not that kind of charge, no. But I mean, you're still charging something, I guess. But this is more like place a temporary charge on an object. That's not that kind of charge. Is different, you know. This is like saying, you know, remember the wool and the rod that I showed you guys that day, and we put the rod into the Faraday cup, and you saw the charge appear and stuff. That's the idea, really. What you're doing is you're not inducing. You're giving, because induction is different. You're giving a charge to that material by contact, by rubbing the two materials. If my hair gains 7 electrons, what does that mean about the balloon? It loses 7 electrons. Remember, that charge can be transferred only via electrons, not protons. Okay, only via electrons. We talked about charging by induction and charging by polarization. By induction, the idea was that you charge an object, bring it near a metallic object or a conductor. The conductor naturally wants to separate. So if I bring a negative charge near something, the positive charges get attracted to the surface. The negative charges all go away. They want to escape. You then connect a cable to ground it. From that ground cable, the extra negative charges flow out. So as a result, it's set up all these positive charges because of this rod. You now remove the rod once that cable is disconnected, and you're left with all positive charges. It's called charging by induction. And then polarization is simply bringing something near another object, causing its poles to realign. Okay, it's a realignment of the poles. But when removed, the actual object will go back to the way it was. Okay, it's similar to the idea of inducing magnetism on an object temporarily, like a weak magnet. What else? I'm trying to think of what else theoretical from 17.1. That's it on theoretical stuff. Let's look at 17.2. 17.2 is where we kind of went into the math that exists for electrical charges. So, first of all, you remember, what's the formula for 17.2? For force, what was the formula? I'm asking because it's very similar to another formula, so I'm thinking some of you might have it memorized already. Alejandro?
It's like Kc or F electric equals Kc times the first charge times the second charge over the radius squared.
Be careful. What's one thing you have to correct himself on?
Kc is like outside.
Same thing though, numerator or outside. Yeah, either way works because it's a multiplier, whether it's numerator or not.
It's not radius, it's distance between the electrons.
Yeah, be careful that R is not the radius here, okay? It's not the
The
radius.
distance between the
Centers of each of the particles, yep. Yeah, Katie.
How do we know when to put it in like times 10 to the negative 9 times 10 to the negative 6? When it gives you like,
Based on the unit, so we'll do an example and I'll show you, but it's based on the unit. So if it's nanocoulombs, that's 10 to the negative 9 coulombs. If it's microcoulombs, that's 10 to the negative 6 coulombs. I'll do an example with both so you can see, okay? So this formula is analogous to what? To what? What does G stand for? Gravity, the gravitational formula. Okay, so the gravitational formula, G m1 m2 over r squared, is very similar. G and K are both constants. M1 and M2 are like Q1 and Q2. They are properties of the actual object itself, its mass or its charge. R squared is the same exact thing in both formulas. It's the distance from center to center. Now, the other thing we have to recognize is that the electric charge can either be repulsive or attractive. The gravitational pole, though, is always attractive. Okay? This can be repulsive or attractive. With two particles, this is a very easy setup. It really is. It's not even worth practicing with two. I'll practice one with three with you guys. But with two particles, like say I had two particles and they're separated by a distance of 5 meters. And the particles are 3 coulombs and 7 coulombs. Well, you put a 5 meters in the bottom, 3 coulombs, 7 coulombs for Q1 and Q2, plug in your constant, you get your force. If you have two particles and they're both positive, what kind of a force is it? If they're both positive. Repulsive, good, they repel each other. If they're both negative, still repel each other. If one charge is negative and one charge is positive, you have attractive force. Okay, so the sign really doesn't matter too much. It's understanding the concept that's involved. Some students in the past have memorized, if I get a negative answer, it means attractive, because attractive can only come about when you have a positive and a negative charge, and a positive here and a negative here would lead us to a negative answer. Now, if you want to remember that, that's fine, but that is only true for a two-particle system. For a three-particle system, we have to consider the fact that we have to look at a free body diagram to understand what is physically happening. Let's look at an example of that. So let's say we've got three particles arranged in the following format. So we've got 7 microcoulombs, 5 nanocoulombs, and 8 microcoulombs as our charges. So we'll look at micro and nano. We have a distance between their centers, the first and second, of let's say 0.5 meters, and then the second and third of 0.3 meters. Okay, 0.5 meters and 0.3 meters. I do not need any other information. I have enough information to solve. Now, the question is, which particle am I interested in? So you have to look at the problem for that. I have not stated that yet. So at this point in time, you could be interested in particle 1, particle 2, or particle 3. You could be interested in any of those particles and determine the behavior of that particle as a result of the other two. Now, I'm going to go ahead and look at particle 2, the one in the middle. All right? I think in class we looked at the particle on the far left, just to mix it up so you can see a different free body diagram. And I'm going to analyze this, but I'm going to use logic. I'm not going to just randomly pick directions. Use logic. So here's what we do. Please look up. Okay, I'm not going to do it on there, so you have to look up to see this. cover up one of the other particles that you're not concerned about. You're concerned about particle 2, so cover up particle 3 for a second. Imagine that particle 2, because you're concerned with it, can move. We're trying to figure out, is particle 2 going to move left or is it going to move right? That's the goal of this question, really. Is the overall force going to be pushing it left or pushing it right? So particle 2 can move. Particle 1 can't. Hypothetically, it can. Okay, what would particle 1 do to particle 2? What would it cause?
Particle 2 to go, right?
Yeah, it would cause particle 2 to move to the right because they're same sign, they're both positive, so it's a repulsive force. So particle 2 would feel a pull to the right, or a push, I guess, to the right. A force on particle 2 from particle 1. This is how we begin this problem. This is probably the most important part. This is the hardest part, what we're doing right now. Plugging in the math is actually quite simple at the end. So again, particle 1 would cause particle 2 to move to the right. Now, cover up particle 1 at this point. And look at particle 3. Which way would particle 3 cause particle 2 to move? Particle 3 to the left. Particle 3 is positive, particle 2 is positive. They're going to repel each other. Since we're making believe that particle 3 can't move, particle 2 would be pushed to the left. A force on particle 2 from particle 3. That's how I label my free body diagram. Okay, again, this is particle 2 that we're looking at. From this point on, it's actually quite simple. You have to do the formula twice, but that's it. All you have to do is that formula 2 times. So to get F23, go ahead, yeah. What do you got? To get F23, Kc I'll give you. It's 9 times 10 to the 9.
And then
Q1, Q2, go ahead.
5. Would it just be 5?
What does nano mean?
Times 10.
Oh, times 10 to the negative 6. Negative 3. Negative 9.
Negative 9. So by the way, look at what I'm doing. I'm calling this is Q2, because look, we're looking at F23. So this is Q2, and then Q3 right here is going next to it. Okay?
8 times 10 to the negative 9.
Be careful, that's micro, not nano. Look at the units. It's hard to see.
It's micro 6.
Good.
Okay.
All over?
1 sec. Over 0.3 squared.
Okay? So again, this, I'll point to it so you guys can see if you're not clear. If you want to write out the formula, you can. This is Kc, Q2, Q3, over R23 squared. Again, Kc, Q2, Q3. Why do I use Q2 and Q3? Because I'm looking at F23. Q2, Q3 over R23 squared. Klaus, then algebra.
What's the name of the term before the C? Is it
This one or the other one? This is micro. This means 8 microcoulombs, and micro means 10 to the negative 6, literally.
So negative n instead of the negative 9.
This is nano, and that means 10 to the negative 9, yes. Okay, Alejandro?
And so just overall for this problem, do you need to find the magnitude of both sides pushing on on Q2, and then whichever one has the more
Force?
Force is
The direction that
decide
we're...
which direction it goes on. So like,
Absolutely.
let's say the left one had more force, would it go to the more to the right?
No, it would go to the left. It goes in the direction the arrow, yeah. So if F23 was bigger than F21, it would go left, because F23 is pulling left. Okay, you're going to do the same thing for F21 and compare those values. Okay, I will record in the other class, so feel free to look at their video also, depending on what they ask.